Welcome to this module, and this is our last module for this particular lecture. In the last series of modules, what we have seen? We have seen a chip that is integrated with a heater, over which there is an insulator, over which there are interdigitated electrodes, on which there was piezoresistive sensors or sensing layers. On there was an insulator, over which there was a gold pad. Now, on this gold pad we will be patterning SU8 pillars. So, the role of this SU8 pillars would be to transmit a force that will be applying to the tissue through the indenter, right. But before we reach to that particular point, let us see how we can pattern the SU8 pillar. So, if you see the screen, what you see is that this particular chip, it has SU8 pillars, right. We have seen until gold pad. Now, how to create those pillars 1, 2, 3, 4, how to create these pillars? To create these pillars, we will be using a technique which you already know, known as photolithography. Okay. And what I want is these pillars I said it is SU8, because these pillars are made up of SU8 or patterned using SU8, they are non-conducting. Why? Because SU8 is a polymer, is a non-conductive polymer. Now, we will say how come polymer is conductive and non-conductive? Polymer can be conductive. For example, we have used P dot PSS, this is a conductive polymer, but SU8 is a non-conductive polymer or an insulator. However, I want these pillars to be the part of the gold pad. I want these 4 pillars to be part of the gold pad. So, when I apply a voltage between this, the current should flow from the pillars to the tissue which is placed on the pillars to the another electrode. We will see how that happens. So, to make SU8 conductive, what we can do? We can coat SU8 pillars with a metal. We can coat SU8 pillars with a metal. So, how to coat SU8 pillars with metal? Either you can use standard photolithography or you can use a technique called as lift off. Either use a standard photolithography or a technique called lift off. Alright. So, you see here in this particular chip, what you see is there are gold pads, there is a gold pad, and there are SU8 pillars which are coated with gold. You can see there is a gold over SU8 pillar, right. Same thing we want at the end of our process flow. So, if I draw quickly what we have until now, is a oxidized silicon wafer on which there is a micro heater, right, on which there is an insulator, on the insulator. Now, this is just a contact pad. There are interdigitated electrodes, right, and on this interdigitated electrodes there is a sensing layer which is our piezoresistive sensor. On this piezoresistive sensor there is an insulator, on this insulator there is a gold pad. So, let me draw gold pad like this. So, what is this? SiO2, SiO2, this is your micro heater, this is SiO2, interdigitated electrodes, piezoresistive, sensing layer, SiO2, gold pad, right. This is what we have seen. Now, on this particular material, on this particular chip, what we have to do? We have to, so I will draw it here, or let me draw it here, that is easy. So, assume that all the layers that we have drawn over here, all the layers are there, and I am just drawing the gold pad. Okay, I am just drawing gold pad. So, below this gold pad, these remaining layers are there. Which layer? From silicon dioxide, piezoresistor, interdigital electrodes, in SiO2, micro heater, and below it there is an oxide. So, I will just draw a line here below which there is an oxide. Okay. Just to make it easier, So, this particular schematic or part of the schematic represents all these 5 layers, which is your silicon dioxide and your piezoresistor and your interdigital electrodes and your SiO2 and your micro heater. Okay. Now, this is our gold pad, we know that, right. This is our gold pad. On this gold pad, I will spin coat SU8, like spin coating photoresist, we will spin coat SU8. Okay. This is gold pad. Just to make it easier, I am just filling this block, so that it is easier to identify difference between your gold pad and SU8. Okay. Now, SU8 is negative photoresist. SU8 is a negative photoresist. So, we all know which kind of mask we have to use, so that we can save the area below which, or save the area or we can save the SU8 on the area that we want to have pillars for, right. So, which kind of mask we can use? If I use a bright field mask, and the pillars are, or the area that is dark field in a bright field mask, the area that are patterns, will it work with SU8, or should I use the dark field mask, where the light can penetrate only in the area where I want to protect my SU8. You get it? So, let us see this. If I draw a mask which has 4 pillars like this, and rest of the area is dark filled, is this mask a better mask? This is my dark filled mask, dark filled. So, if I use dark filled mask to form SU8 pillar, does it make sense? Because SU8 is a negative photoresist, SU8 is a negative photoresist. So, if I use this mask which is dark filled, assume that these lines that we have drawn here, this everything is dark, okay, and only in the area where you can see the circles it is brighter. Now, what is the characteristics of SU8 or negative photoresist? That the light or the area that is exposed, the area which is exposed will become stronger, the area which is not exposed with UV light will become weaker, we know, right. So, negative photoresist, the area which is exposed with UV will become stronger, and in positive photoresist, the area which is exposed with UV will become weaker, So, we have to use dark field mask with SU8 to form the pillars, right. Now, so after spin coating SU8, there is a data sheet that you need to follow how to use SU8 as a negative photoresist. In case of positive and negative photoresist, what we have learned until now is that the first step is after spin coating you have to do a soft bake, followed by UV exposure. So, alignment, mask alignment followed by UV exposure, followed by PR development, followed by post bake or hard bake, right, hard bake, and so on. This is what we have learned until now for positive and negative photoresist, right. In case of SU8, SU8 is similar to negative photoresist, but the process step is little bit different. So, what is the process step? After SU8 we coat the SU8 on this chip, we first go for soft bake, which is done at 65 degree centigrade, followed by UV exposure, followed by hard bake, followed by photoresist developer. What I said? After SU8, which is our negative photoresist, soft bake at 65 degree, this temperature is given in the data sheet. For how much time you have to soft bake is also given depending on the thickness of SU8. So, when you look at the data sheet of SU8, you will see the temperature, the thickness, the soft bake time, the hard bake time, and same stands true for negative and positive photoresist as well. So, when you look at the data sheet, you will know these numbers, but the one thing that is different than positive and negative photoresist compared to SU8 is that here after soft baking at UV exposure, we are going for hard baking instead of photoresist developer. This one step you have to remember, alright. So, that is only different. Here you see there is a photoresist developing and then hard bake, here it is hard bake and then photoresist developer. So, that thing is one thing that you guys have to remember in case of SU8. So, I will use SU8 with my dark filled mask. I will use SU8 with my dark filled mask. You now know why dark filled. So, after SU8 what we will do? We will perform soft bake, we will go for soft bake, then we will go for UV exposure, followed by hard bake, UV exposure followed by hard bake, followed by PR developer. Okay. So, if I perform this step soft bake, then I use here UV exposure. When I say UV exposure, it is understood that there is a mask that we will load and then we will align and then followed by a UV exposure. Next step would be hard bake, next step would be PR developer. When we perform all these steps, what we get? We get, when you perform all these steps, we get, you look at this particular diagram. Okay. What we get is, or because two pillars on the back side, assuming that two pillars on the back side cross section, we get SU8 in this particular fashion. Why? Because we are taking a cross section of this, right. So, that is why we are representing only two pillars are on the back side of these pillars. You got it. So, this is just a negative photoresist. After this, you have to go for annealing this particular chip at a higher temperature. So, let us say at 130 degree centigrade or 140 degree centigrade. We have to anneal the chip at higher temperature to make the SU8 harder, You got it. So, this is how we pattern the SU8 on the chrome gold pad. Things to remember is SU8 is a negative photoresist and compared to the positive and negative photoresist, the only difference is that instead of going for PR developer after UV exposure, we have to go for hard bake followed by PR developer, right. So, after we learn this, what we will learn now? How we can coat the SU8 with metal, right. So, we will see how we can coat the SU8 with metal in the next module, or actually let us finish in this module, because I want to teach you something in the next module. So, in this particular thing, what we have done until now is we have created SU8 pillar. So, now let us see what is the step that we will do to make the SU8 conductive, alright. So, if you see the screen, what we have is SU8 pillar in this particular fashion. Now, there are two ways, okay. One is I am just drawing a chip so that it becomes easier. Just concentrate on these two figures, right, and let us directly draw SU8 pillars here. There are other layers below it, okay. We start with SU8 pillar. On this SU8 pillar, I deposit chrome gold, right, and make it conductive, But if I do this, right, I have to perform a photolithography, standard photolithography to pattern the chrome gold in a way that it should only coat SU8 like this, correct, and remaining area I do not want to coat it with any other metal. But if I deposit chrome gold and if I perform standard photolithography and I want to protect only in this area, then below these pillars, what was that? Below this pillar there is a gold pad, right, below this pillar there is a gold pad. You are with me, right? This is exactly this figure, and below this there is another layers. So, if you compare this one, what we have done is we have to coat the SU8 pillars without coating this particular area, otherwise everything will be shorted out, right. So, if I perform a standard photolithography, what will happen is the gold in this region will also get etched, So, what will happen is it will look like this, you see, in this case it will look like this, but this is not what we want. We want a single gold pad below SU8 pillars, right, because see chrome gold we are depositing, which is here, there is a chrome gold below it, which is like here, like, and then if I perform standard photolithography and if I just want to coat the SU8 pillars, then this region will get etched. So, in that case what I can do? I can perform not soft lithography, I can perform lift off technique. What is called lift off technique? So, let us see how lift off technique can be done. Lift off technique. So, I am only drawing SU8 pillar and gold pad, right, and you guys have to you guys have to assume that there are other layers below the gold pad. There are other layers below the gold pad. So, let us see. All right, right. So, this is the starting wafer where this is your SU8 pillar. In case of lift off, what we will do is we will coat this SU8 pillar and every area of the wafer with a photoresist. So, we will spin coat positive photoresist. We will spin coat positive photoresist. This photoresist is thicker compared to our earlier positive photoresist. The idea of keeping this photoresist thicker is that here we want to use a lift off technique. So, for lift off technique we have to use a photoresist which is thicker compared to normal lithography techniques or standard lithography techniques. So, once I spin coat photoresist, what is the next step? Next step is I will pre-bake the wafer at 90 degrees centigrade, right. Next step is I will load the mask, and this time I want to open only the area which I want to make it conductive, that means the area which is surrounding SU8 pillar. So, what does that mean? That I will have a mask that will be a dark field mask, with only area, the circular area you can see here, right, that is bright field, that is pattern. So, only the circle, through the circle only light can pass. Now, why this? Why I have to do this? So, you see here, if I load the mask, right, such that I am loading the mask such that the photoresist is protected only in the area which you can see right over here, which is dark red, and in this area photoresist should not be there. So, I will have a mask which looks like this. This can be my dark field mask, Okay. Now, what I will do? I will go for soft lithography. Sorry, after this we will perform UV exposure, or we go for UV exposure. All right. So, after UV exposure, what is the next step? Next step is photoresist developer, right. So, when I will develop my photoresist after performing this step, what will I have? I will have SU8 pillar, right, and everywhere there will be photoresist. So, I am just drawing photoresist to save time in this fashion. This is gold pad, this dotted version is a gold pad and this is SU8 pillar, right. So, this is my photoresist, right, because we have used dark field mask, the positive photoresist. So, area which is not exposed will be stronger, area which is not exposed will be stronger. Now, you see here that what is there? There are SU8 pillars, there is a positive photoresist and here is a gold pad and below there are other layers. So, the next step is I will deposit chrome gold on this particular chip. This is my chrome gold. See, this is chrome gold. Now, see the beauty of lift off. After depositing chrome gold, I will put this chip, I will put this wafer in, I will load this wafer or dip this wafer in acetone, right. So, I will dip this wafer in acetone. What will happen is acetone will lift off the photoresist, acetone will strip the photoresist, right. You know acetone is a photoresist stripper, it will strip photoresist. When it strips photoresist, the metal on the photoresist will also get stripped. When acetone strips photoresist, the metal on the photoresist will also come off, right. And what we will see is a wafer with a gold pad, SU8 pillar and SU8 pillar coated with chrome gold. Why? Because see photoresist from this area will be and from this area, right. These 3 1 2 3 all 3 area will be stripped off and the metal on the photoresist will be lift off. So, we lift off the metal on the photoresist and thus we get SU8 pillars, you can see right over here SU8 pillars and on SU8 pillars there is a chrome gold or a metal, right. This is how we perform lift off. Here there is no tension of performing the whole steps for standard lithography, that is you spin coat, then you load the mask, then you spin coat, then soft bake, then load the mask, then develop the photoresist, then you go for a hard bake and then perform chrome gold etchant, right, and then finally go for photoresist stripping off. Here the idea is that you spin coat photoresist, you pattern the photoresist and you deposit chrome gold and you dip the wafer in acetone. So, the life becomes extremely easy because acetone is a stripper, it will lift off the metal on it and thus we directly get SU8 pillars that are coated with metal, right. So, if I do this kind of stuff, what will I have? I will have a chip that is ready with SU8 pillars that are conductive because there is a metal coated on the SU8. Now, one thing that we have to remember in this particular application, if you remember the lithography and the physical vapor deposition, in particular thermal evaporation or E-beam, if you use thermal evaporation or E-beam, what will happen? There is a cons of E-beam, there is a drawback or limitations of E-beam or thermal evaporation. What is that? There is a, it cannot or it has a poor step coverage. So, if this is my SU8 pillar and if I am depositing a metal, right, if I am depositing metal, it will not cover this area or maybe it will not cover this area. This is my gold pad, right, this is my gold pad, this is my SU8 pillar and if I am depositing metal, it may not cover this area because of the poor step coverage. poor step coverage in the case of thermal evaporation or e-beam evaporation. So, but if I tilt this wafer, right, if I have wafer like this, if I tilt the wafer, what will happen? It will deposit on this particular area, right. You see this particular area will also get coated along with the tip. So, now if I tilt the wafer, I will have one side coating of SU8 pillar, this is gold pad. So, this becomes conductive, the path is conductive path from tip to the gold pad. If I use like this, there are chances that the steps here would not be covered. Say SU8 pillars, if there are 4 SU8 pillars, they may not get covered uniformly, and that is why the idea is that we should at least have a conductive layer from the tip to the pad, and that we can do by just tilting the wafer in one of the direction, either in this direction or that direction. You can use 45 degree if you consider this one as a flat, you just put an angle, and at that angle you can cover at least one side of the SU8 pillar. So, if you see the chip, how the chip will look like? Now, the chip will look like the one shown in figure over here, right, and this chip has what? This chip consists of, now it consists of a electrode, a gold electrode with SU8 pillars that are conductive. This is a gold electrode, correct, and what it has, it is also integrated with micro heater, it is also integrated with piezoresistive material, right. So, in that case what we will do? We will see how this chip can be used to understand the properties of tissue. So, since this chip has a heater, if I use a 3D printed case as shown here, 3D printer, okay. If I use a 3D printer to create a case which is shown right over here, and if I am using a chip which is integrated with a heater, you can see this funnel, right. If I place the tissue in this funnel, this tissue like this tissue will be placed or will be touching the chip, center of the chip. Now, I have a indenter, you can see here I have a indenter and there is a thermistor on the indenter. So, if I heat the tissue from the bottom, I can measure the temperature of the tissue at the top, right. So, I have a temperature T2 here, temperature T1 here. If I know the difference between T1 and T2, I can measure thermal conductivity of tissue, right, one thing. Now, we know that there is a electrode, which electrode? Electrode that consists of a gold pad along with SU8 pillars which are conductive. So, we say this electrode number 1, electrode which is consists of a gold pad and SU8 pillars which are conductive. If you see the indenter, that we will press it, right, we have to press the tissue. You see the indenter here, indenter has another electrode, let us give this electrode as number 2, name as number 2. So, we have electrode 1 on chip, electrode 2 on the indenter. Now, if I apply voltage between this electrode and the top electrode, that means electrode 2 and electrode 1, what will happen? Corresponds to the resistance of the tissue, or corresponding to the resistance of tissue, the current flowing through the tissue would be different, right. See, I am applying voltage across this terminal. So, I will apply a voltage across tissue in this particular fashion. Corresponding to the resistance of the tissue, I will be able to see change in current, right. So, now I can measure the electrical property of tissue. electrical properties of tissue. Next, we know that the sensor or the chip consists of piezoresistive sensing materials, right. It consists of piezoresistive sensing materials. So, if I have a indenter and if I press the tissue, then the piezoresistor on the chip will have or will experience certain amount of force depending on my indentation, how much I am indenting the tissue, and that force transmitted from the indenter to the chip depends on the elasticity of the tissue, is not it? Elasticity of the tissue. Again, there is a indenter, we are indenting the tissue with some micronewton to millinewton of force. How much force will be transmitted on the chip depends on the elasticity of the tissue. Now, the amount of force that is transmitted on the chip can be measured if the chip is integrated with some sensor, and our chip is already integrated with a piezoresistive sensor. But there is a catch here. Until now what we have seen, if you see this slide, we have seen that we have everything below SU8 pillar like interdigitated electrodes, sensing layer and micro heater, everything. But if I let us say if I draw a piezoresistive sensor, let us say this is a piezoresistive material, okay, PZR, piezoresistor. If I apply force, what will happen? This sensing layer should feel some force. That force, how much force it feels depends on the elasticity of the tissue. But this piezoresistor sensor will not be sensitive because we are using silicon chip, and silicon is hard material. So, there will be no strain in piezoresistor, there will be no amount sensitivity of piezoresistor will be extremely small. So, how to improve the sensitivity? We can improve the sensitivity if I create a diaphragm. In this case, when I apply a force, right, to the tissue with the help of indenter, I will be looking at the change in the elasticity, of tissue based on how much force is transmitted onto the chip that is integrated with my piezoresistive sensor. That means that this is a indenter. If I indent this on the tissue, right, and if I know that there is let us say 10 millinewton of force that I am applying on the top, how much force is there on the chip depends on my resistance of the sensor. This when I apply force, this will bend, and this bending will cause change in resistance, and this resistance corresponds to the elasticity of tissue. Got it? So, now what we can do? We can measure the electrical, mechanical and thermal property of tissue, that is what we have written here, electrothermomechanical phenotyping of breast cancer, because the tissue that we can try is a breast cancer tissue. That does not stop you to use any other tissue. You see, you can use any tissue related cancer, and you can try with this chip to see whether the tissue has as the cancer progresses or as the disease progresses, are the parameters or property of tissue different. Is the mechanical property of tissue different, that is elasticity is different, or is there resistance is different, or thermal conductivity is different. So, this is not limited to just breast cancer, it can be used for oral cancer, can be used for liver, can be used for any tissue related cancer. You got it. So, this kind of chip we can use to understand the electrical, thermal and mechanical property of tissue. Now, you know that after looking at several modules, we are able to understand what is the process flow for developing a biochip that can be used for measuring the ETM properties of tissue, right. So, just to help you out how it should look like. So, what is the next step? Now, this everything is using the piezo actuator, this and that, but can we design a device that is small like a pen, and it has everything. how can you squeeze it down, right? How about I hold the device on my palm and I can just put a tissue, and so when I am saying it should be holded on the palm, does not mean it can be always held on the palm. That I mean is that what I mean is that the size of the device should be very small, portable, right. See, once you understand that the tissue properties we can measure, now let us try to understand how we can reduce the cost. Not everything is important in microengineering or MEMS devices or devices for clinical research that the cost should be down. One thing is a performance, sensitivity, accuracy, resolution, and then everything is figured out. Now, can we bring the cost down? This is our research approach should be, right. So, you see the slide, this is how it should look like. This is what I think that okay, can we bring it to a palm size device. This is the indenter, you can see very clearly, this one is a indenter, and this indenter you can see here is attached with a gold pad, it has an electrode, and then this is the 3D printed device on which there is a chip, and it is a palm size device, a handheld small device. Now, this particular application does not require this device to be handled. The idea of showing you this schematic is only to make sure that the device that we are designing should be small enough for portability point of view. Now, always like I said, it is not always that we have to go for it, but it is better to have a smaller device. You see, we have a phone which was really longer, right, cell phone, we are bringing down, bringing down, bringing down. So, we are making a small chips, where we are making things down easy, easy accessibility, easy portability and better operation, right. So, this is the end of this particular module, and what we saw in this whole lecture, which is divided into several modules, is that we learn a process flow to create a chip that is integrated with 3 different sensors, and the idea is to understand the ETM properties, that is electrical, thermal and mechanical properties of tissue. And the bigger idea is that we with this particular modalities, that is electrical, thermal and mechanical modalities, along with MRI and mammography, right, can we help, can we aid the clinician or a path lab to take a decision, right, can we help or aid the clinician or a path lab to take a decision to reduce false positive and false negative signals in case of cancer. That is our bigger goal. Alright. So, we will continue in the next lecture and look at other kind of application of the sensor and how these sensors can be used to solve a very important problem in clinical perspective or from the clinical perspective. Till then, you take care, I will see you in next lecture.